In section 4, here we have the tangent problem and the velocity problem. So those are kind of some of the things that kind of have to deal with calculus, and kind of the reason that we are using calculus is to solve these type of problems. So the first one is the tangent problem. So a tangent is a line that crosses a curve. Once, so it only crosses it once and goes in the direction of the curve. Direction of the curve. Okay, so if we have say circle or something like that, it's going around. A tangent would be, it would only touches it once, crosses the curve only once. So, or maybe not, maybe I shouldn't use the word crosses, maybe it touches the curve only once. So it would go through here and it's only going to touch that once. So you think about, like, when people say they go off on a tangent, it means that when you're in a conversation, right, and somebody mentions yeah, I played football, and then somebody starts talking about that, oh, their favorite team of football is the Buffalo Bills, the best team ever in the world, the greatest. So here we have a curve, here's our point. So to cross it once would be like this, right? So that would cross it once. It might look like it only touches it once through that point, right? I'm only touching that point once. But if I go, say, here, that would cross it twice, right? So if it crosses it twice, that is called a secant. A secant is when it crosses it twice. So secant is when it touches it twice. So it only can touch the graph once and goes in the direction of that curve. And so that's a tangent. So the problem that we have is, so if I have like this example here, and I want to find the slope of a point that touches my graph at 1, 1. So here I have a graph, 1, negative 1, 1, negative 2, 2, and 4. Right, so here's the parabola, 0, 0. So if I want to know what the tangent, the slope of the tangent line at this point 1, well, my graph is only going to touch that. My line is only going to touch that once. So the problem is, if I want to find slope, or the formula for slope is y2 minus y1, correct? So that means I need two y values, x2 minus x1. I need two x values. Well, I'm only given 1 point. So we could go ahead and estimate and say, well, okay, let's do a secant, right? Let's do a second point, like 2, 4. And let's go ahead and find what the slope is of this line. Let's change the color, maybe like green here. So that doesn't look exactly like that first line, but it's kind of close. So we can go ahead and find the slope with a second point. So I just plug in 2 into this and square it, and I get 4. So my second point is 2, 4. And I can go ahead and find the slope of that. All right, 4 minus 1 over 2 minus 1 is 3 over 1. So that slope is 3, right, of the green one. So then we could get maybe a little bit closer. I could put in maybe, let's see, I could put in maybe a half, and I'm up here, right? So maybe this line, let's see, maybe pink, this line right here, maybe looks a little closer to that one. And then maybe I could get even closer than that, maybe really, really, really close. And that line definitely looks like, oops, that's not that one, definitely not that one. This line really looks like, because it's going through both of those, really looks close to that first line. My parabola is not the greatest, so that's why the lines kind of don't look on top of each other. So maybe I plug in to my equation, y equals x squared. I plug in, how about 0.01? So that's really, really close to 1. And then I go ahead and square that. and I get 1.0201. So then I take my y's and subtract them over my x's, 0.01 minus 1, and I get 2.01. So that's really, really close. So then I could even go closer, and I could plug in 0.001, and maybe I plug that in, and my slope becomes 0.001, and it's going to keep on doing that, right? So what value is my slope approaching? Well, if I keep on doing that, I'm going to see that eventually it's going to be like 2.000000001, right? So really, my slope of this tangent line is approaching 2. So as I get closer and closer, right? As I get closer and closer to my x, and I plug that in, get my y, I get closer and closer to this value of 2. So that's the idea of a limit. So the limit of my slope as I get closer and closer to the x value, so as I get closer and closer to my x value, closer and closer to x value, closer to x value, then my slope is getting closer and closer to, that's where the equal comes in, that's where the answer is, closer to 2. So that's what this is saying. As I get closer and closer to my x value, the limit of my slope, or what my slope is, what I'm getting closer and closer to as I do my formula, right? As I do the slope formula, my value gets closer and closer to 2. The next problem that is solved by calculus is the velocity problem. Now this is very similar to the tangent problem. It's just kind of the context is different, right? So if we drop some ball off a building, so we have some building, some Canadian building, so who knows what it actually looks like. It's Canadian. It's crazy. They're crazy. So I drop some building, and it's 450 meters high, and we want to find out what is the velocity of the ball. So as it drops, right, as it drops, it's going down, and it has a velocity all the way down. So we want to know at 5 seconds, at exactly 5 seconds, what is the velocity of the ball at that time. So usually when we find velocity, we were talking about speed, right? And speed equals distance over time. And so in order to find that, we usually we use our beginning and our end, right? How far we go totally, right? Our change in our distance over our change, how long it takes us to get there, right? Change in time. So those aren't F's, those are T's. Kind of look like it. Okay, so it's the change in our distance over the change in time. But so normally we need two distances, right? What we start out, so like at 450, and how far we're going, right? And how far it travels down. So say 300, and then we divide that by how long it takes, and then we can find our speed at that time, right? So maybe at 0 time, and then it takes, say, 5 seconds, right? And then, so then we go ahead and subtract that, and we get 150 divided by 5, so we get 30, and it's negative because we're going down, right? Because this is negative. And so 30, say, meters per second, right? Negative 30 meters per second. Well, is that really the actual speed at this point? At this point right here? Or is that just the average speed from this distance to this distance? That is just the average. That's the average speed. Well, how do I find the instantaneous speed, the speed exactly at 5 seconds. Well, what I can do is I can just get closer and closer to that height at 5 seconds. So I can get closer and closer to that height at 5 seconds. And the closer I get, say that is 300 at 5 seconds, that's at 300. And so then I just want to get closer and closer to 300, at 305, and maybe that's at 4.5 seconds. And then maybe I want to get even closer. How about 301? And maybe that's 4.8 seconds. And so I keep on doing this until I can get closer and closer, maybe 300.9 or 300.001, right? Because that's just barely more distance than 300. And so then I would get closer and closer to this 5 as well. So maybe it's like 4.99 seconds that it takes to get to that distance of 301.01. So it's really almost the same exact problem as your tangent problem. Basically, we're just finding slope, right? The change in d over the change in t. That's the same thing as change in y over the change in x. X just has to deal with your time, and y just has to deal with your distance. So we just want to get closer and closer to whatever our distance is at 5 seconds. So we could go ahead and use this formula for distance, right? 4.9 t squared. So we can go ahead and use that in order to find that. So I could do the plug in our time, 5 seconds, see what the actual height is, instead of just guessing like I did. So I could plug in 5 square, I get 25 and 25.49. So we get 122.5 meters. So that's the height, right? So if you're in physics, you'll probably talk about this a lot, and you might have already done it. Sometimes if you're taking physics at the same time as this, we'll hit things that you talk about in physics before physics does, and sometimes physics will hit stuff before calculus does. So I have 122.5 meters, and maybe instead of doing 450 feet, we can just say, well, when I'm holding the ball, let's say that is at 0. That's at height 0, right? Because I'm just dropping it down. And then at 5 seconds, we know we're at that. And then at time is 0. So you kind of go a little bit in reverse. So this is our, say, initial height is 0 at time 0. And then we go ahead and subtract this. So again, this would be our average speed, right? So from 0 to 5 seconds, it would be our average speed. So to find instantaneous speed, that's when we're going to have to go closer and closer to that original height, and closer to our time. That's not the right. So 24.5 meters per second. That would be our average, right? So then I would just want to get closer and closer to this time of 5 seconds. So how about 4.9? So I want to times 4.9, square that, and then times by another 4.9 to find our height, right? That's going to find our distance. So we get 117.649. Okay, and we'll take that away from our height at 5 seconds because we're just getting closer and closer. And that's over 5 seconds minus, I plugged in 4.9. So now we can do the math here. So we get 4.851 on top, and then on bottom we get the 0.1. And then so we just divide that, move it over, and we get, just move the decimal over 1, and we get 48.5, or 51. And then so that's meters per second. And then so as I get closer and closer, I could do 0.99, and then maybe 99, and 99, and keep on adding those 9s in there. I would find my heights, and I would get closer and closer to that value in order to find that velocity. And so as you do that, you start to approach 49 meters per second. So the limit of that, the limit of your kind of slope equation, which is basically what it is, right, is 49 meters per second. So the velocity and your slope are really the same thing, because you're just finding either your change in y over your change in x, or you're finding your change in height over your change in time, or change in distance over time. So really they're the same exact problem that you're dealing with. So that velocity that we just found is called instantaneous velocity. It's the same thing as we're trying to find, we're trying to find the slope of a point. Well, we just get closer and closer to that, right? Because if there's two lines crossing, then it's called a secant. If we just have one, then it's just the tangent line. And instantaneous velocity, we're trying to get exactly at 5 seconds, right? If we have to get closer and closer, well, that's using two values and averaging that. So the average velocity and the secant are the same. Why do I do that? I don't know. Velocity. And whatever, you know how to spell velocity, I don't. And then average velocity and secant are the same. And instantaneous velocity, the velocity at that second, at that instant, is the same as the tangent line. So that's kind of how they're related.